Welcome to Saturday Morning Physics and to today's Van Loo family presentations. I'm Physics Professor Tim Chupp, one of the organizers of Saturday Morning Physics, along with my colleague Professor Rachel Goldman. And today, this is the last Saturday Morning Physics of the academic year, so I want to take a moment to recognize the efforts and the contributions of the program coordinator, Carol Raybook, who's in the back. And the amazing Monica Wood, who's here. And her staff of the Warren M. Smith Demo Lab, Nick Arnold, who's also here, and Connor Heaney, and also Case Wolfenstorf, who helps Carol and is also here today. Today's Saturday Morning Physics is made possible by a generous gift that established the Van Loo Family Endowment with the express intent of supporting these student presentations. I also want to express the gratitude for the Dr. Mary Lois Tiffany Endowment and the Pulakeshi Dayalu Astrophysics Fund. And today I want to take a little bit of time to acknowledge the Hideko Tomizawa Endowment, which was established by the family and the longtime partner of Hideko, Yukio Tomizawa, who died earlier this year in January. Yukio was a theoretical physicist by training, but he was insatiable in his curiosity, and with boundless energy and enthusiasm, he approached everything in life, in particular physics. I met him at the very start of my career here at Michigan, and he would come to me regularly to ask about experimental techniques which I was supposed to be expert at, so that he could propose and, in fact, sometimes himself build experiments to test his ideas. In particular, he set up a particle detection with tons of lead bricks as shielding that he must have stacked himself. Yukio and Hideko were regulars here at Saturday Morning Physics, sitting near the front of the room in rapt attention. And he had a large family, including 9 graduate children, excuse me, I said grandchildren, graduate students, grandchildren. Any of you graduate students? There we go. Okay, well, they're here today, a large number of them, 11 of them here in the front row, and they've come to attend this Saturday Morning Physics. So welcome to you, and thanks so much for your family support. Many of them have come from a long distance, as far away as California and, in fact, Tanzania. So that's a wonderful effort, and welcome. We're really glad that you're here. Before moving on to the presentations, I want to note that today's event will include the traditional Saturday Morning Physics question and answer session. So for those of us joining us online, Monica will write the email address physics@umich.edu, near the bottom, I think. I'll keep talking. So today, the first presentation will be from Tayari Coleman, Ty. He's a third-year Ph.D. candidate in our applied physics program, working at the Center for Ultrafast Optical Sciences, or QOS, on the North Campus here at the University of Michigan. He grew up in the San Francisco Bay Area, and he attended Cal State Chico. And in 2021, he came to the Midwest and to Ann Arbor to join the University of Michigan, and has been working in the lab of Professor Almantas on our North Campus. And he'll tell us about his research today. Ty is also part of the University of Michigan Willie Hobbs Moore chapter of the National Association of Black Physicists, and he's dedicated to outreach, which is how we met. And I should mention that in addition to his pursuits of research towards his Ph.D., Ty is an enthusiastic hiker, and he counts entrepreneurship among his hobbies. The second presentation will be from Max Jerdee. Max is a fourth-year Ph.D. candidate here in the physics department in the complex systems program. He works with Professor Mark Newman, who has been a Saturday morning physics regular presenter. Max grew up in New Jersey, and he attended Princeton University before coming to Michigan. He's also active beyond his complex systems research as the social chair for the Physics Graduate Council, and he enjoys cooking, which sounds like it should lead to banquets for lots of hungry grad students. So thanks for joining us today for this year's Van Loo family presentations. You ready to go, Ty? Okay. I will tell us about making powerful lasers more powerful.
Hello, hello. Hello, everybody. Thank you for coming out on this fine Saturday. So, again, I'm Tayari Coleman, a third-year applied physics PhD student here at the University of Michigan, and I work under the guidance of Amantis Galvanauskas. Today, I'll be talking to you all about how to make powerful lasers more powerful. Before we begin, I'd like to give a special thanks to the Department of Energy, as well as the National Science Foundation and the Center for Ultrafast Optical Sciences for either funding or hosting this research. So, this talk will begin with some background, and we'll go over the terms that we'll need to utilize as we propagate through, and set the scales for what we'll be discussing. Then we'll go over the ultrafast laser systems themselves, what comprises them, what are some examples, and what their future uses will be. And then we'll get into my research, what my research group does, and in particular, what I do. So to start it all off, when I talk about high energy or ultrafast or high power, what do I mean? So high energy, I'm referring to energies of greater than a joule. And that doesn't sound like a lot. A joule is about the energy it takes to move an apple 3 feet into the air. So we can all do that. But when you take that energy and you squeeze it into a very short period of time, you get incredible power. And this period of time I'm referring to is on the scale of hundreds of femtoseconds. So let me get a little presenter here. That is a 1 with 12 zeros in front of it. That is 1 trillion times faster than the blink of an eye. And we put this energy into that time duration to get powers on the order of terawatts and up, is what I'm referring to when I say high power. So that is 1, followed by 12 zeros as well, with a terawatt per scale being twice the annual average US power grid's consumption. So I'm referring to peak power and instantaneous power here, and that's average power. But just so you get some scales of what we're working with. We build these systems to promote high-intensity laser matter interactions. On the bottom here, I have a picture of a laser Wakefield accelerator. This is the primary use of the systems that my team works on. Here we can see a bubble, and what we do is we can push this bubble through plasma at nearly the speed of light. We can trap electrons in these bubbles and accelerate them to massive velocities and thus energies. And all this happens in the space of maybe 8 or so centimeters. And on the right, we have high harmonic generation. And essentially what we can do is we can take a short pulse of a given wavelength or color of light, interact it with a particular material in a particular way, and out comes many more different colors of light with repeating structures in their prevalence. The applications of these systems are very wide, and this is a non-exhaustive list, but there are medical applications with high-resolution X-rays and targeted radiation therapies. There's homeland security with the ability to scan objects to look for maybe hidden dangers or things that may not be safe. Materials processing on the nanoscale, but also with things like laser cutting or laser welding. There are the material sciences. We can look at how these beams interact with solid materials and what happens then. There's ultrafast microscopy and spectroscopy. We can look at molecules at very fast time frames with high resolution as well. And fundamental physics interrogations, which we'll be talking a little more about later. To start it all off, this all starts with the laser, which some of you may know is actually an acronym. LASER stands for Light Amplification by Stimulated Emission of Radiation. And really, what a laser is comprised of is a gain medium or active medium, a resonant cavity, and feedback. So when I say gain medium or active medium, this is really a medium which amplifies a specific wavelength of light that passes through it. And when I say resonant cavity, in this case, it is formed by these two mirrors, which are very carefully tuned to be a particular distance from one another. And here, feedback just means making one of these mirrors partially reflective, so light is able to leave the cavity. By tuning these mirrors to the right length, we are able to get standing waves in these cavities. These standing waves are reinforced through constructive interference. These standing waves are no different than waves on a string. Think of playing the guitar or the piano. It's the same concept, but here with light. Now, the difference between a laser and, say, an incandescent or fluorescent light bulb is that all of the light coming out of a laser is both spatially and temporally coherent, meaning that all of the waves point in the same direction, and they are all in phase with one another. They also all have the same polarization, but we won't be talking about that here. So now we have a laser, and now we need ultra-short pulses. We'll talk about what comprises those. The first term we need to discuss is bandwidth, and this refers to the width of a spectral distribution. And broad bandwidths are needed to make short pulses. And this is true for any signal, whether it's electrical or audio as well. If you want to make something short, it needs a wide array of frequencies or wavelengths. This picture on the left here shows two different waves interfering with one another, one with lambda 1, wavelength 1, and one with lambda 2, wavelength 2, which are not the same. And here we can see they constructively interfere and destructively interfere, generating this beating effect. This beating effect here we can refer to as the envelope. And if we were to add more waves with different wavelengths to these two, we would actually see this envelope begin to get smaller and smaller and shrink. And that, in essence, is really what comprises an ultra-short pulse, is a broad spectral bandwidth. On the bottom left here, I have an example of a spectral distribution. This is a Gaussian distribution. And when I'm referring to a bandwidth or a temporal duration, I'm referring to its full width at half maximum. So we take 50% of the peak power, and we look at the width at that point. So delta lambda, the full width half maximum, and delta t at the full width half maximum. And I have an equation here on the bottom which shows their approximate relationship. But what's really important is that the time of the pulse is inversely proportional to its bandwidth. If you want the pulse to get shorter, you have to increase the bandwidth. And on the right here, I have two more quick equations. Everyone's aware of the speed of light, 186,000 miles per second. But when dealing with ultra-fast optics, two different velocities or speeds become important: the phase velocity and the group velocity. The phase velocity referring to the speed at which the field propagates through your material, and that's determined by the index of refraction. And the group velocity, which is the speed at which the envelope from this beating pattern moves through the material. And in ultra-fast optics, these are often not the same. So now we talk about dispersion, and we start manipulating these pulses of light. There are two types of dispersions which are important in this discussion. Material dispersion. Here I have a white light source, which is comprised of many different colors, as white light is. Anyone who's seen a rainbow or seen a prism before knows that with dispersion, which is a wavelength-dependent the wavelength dependence of index of refraction is material dispersion. We can get a spread over our wavelengths. It's the same effect that creates rainbows, except it happens in water and raindrops. That was material dispersion, and then there's diffraction, which is the angular dependence of the propagation of different frequencies. So if you look on the left wall over here, we have a red and a green laser beam. If I take a diffraction grating and put them in front, we can see that they don't line up everywhere anymore. In fact, the red light is traveling a slightly longer distance than the green light. They have different angles of propagation. And what's important about both of these effects, which start spatially, is that we can use them to change the duration of our pulse in time. And this is what we call in the ultra-fast optics community group velocity dispersion. Both of these effects can lead to temporal dispersion. And the devices we use to do this are called stretchers. On the bottom here, I have an example of two, one using a prism and one using a grating pair. So we can use the material dispersion of the prism here to spread our wavelengths out in space. And as you can see, the red light travels a shorter distance than the blue light. So when we combine these again together, our group velocity is the same, but it's become dispersed. It's spread in time. And this happens both with gratings and with prisms. Now, this is a very profound physical effect, and its use and utilization is what got Gerard Mourou and Donna Strickland awarded the Nobel Prize in Physics in 2018 for their chirp pulse amplification architecture. Now, this is still the mainstay way of amplifying ultra-short pulses of light. And in essence, just as we talked about, you start with a short pulse, you stretch it out in time, then you amplify it, and then you do the exact opposite and compress it back in time, and now you have a short pulse with a lot more energy. Now, we do this because if you don't stretch your pulse in time and you just try to amplify an ultra-short pulse, a whole myriad of nonlinear effects occur, which we want to avoid. And these can range from sending your pulse in and just getting noise out, all the way to sending your pulse in and your amplifier explodes. Definitely not something you want to happen. And it's because of these high peak powers, when you begin to add more and more energy to them, the materials that we're using simply can't handle those kinds of interactions. So we stretch them in time. And when you stretch this pulse here, an important note is that you get a variation in the wavelengths in time as they approach you. This is called chirp. So in this pulse, I have an example. We can see the longer wavelengths lead the shorter wavelengths in the pulse. And we can hear what a chirp sounds like audibly. Well, that's enough of that. But as you can tell, the longer frequencies led the shorter frequencies in that audio file. There are many different systems around the world who utilize the chirp pulse amplification architecture. I have here some of the largest, not all of them, but some of the largest. We have Zeus at 3.3 petawatts peak power. We talked about terawatts, 1 followed by 12 zeros. A petawatt is 1 followed by 15 zeros, so 1,000 times more powerful. Zeus is here at the University of Michigan. We have Solf in China at 12 petawatts, Texas petawatt at 1 petawatt, and Eli over in Europe at 10 petawatts. And these range in energy from many tens of joules, with Zeus 75 joules, all the way to kilojoules with Eli. It just depends on your pulse duration and the peak power you want to achieve. But of course, since Zeus is here at the University of Michigan, I will be going into more detail about Zeus. So Zeus is also an acronym, and it stands for Zettawatt Equivalent Ultra Short Pulsed Laser System. And they really stretch this acronym, we all know. But its predecessor was named Hercules, so there was motivation to continue the lineage. This plot on the left here, I'm referring to intensities in this plot. So we have power, which is energy per time. Intensity is power over area, power per area. So this is the focused beam when we focused it down to a point. And this point could be the size of a widths of human hair, micron, tens of micron level sizes for these beam wastes. The goal with Zeus, in short, is to squeeze enough energy into a small enough space such that we can spontaneously create matter. We've all heard of E equals mc squared, and this is that. We want to use energy to create matter. The scheme that'll be used to achieve this is to take some of that big, powerful 3 petawatt beam, to use some of it in a Wakefield accelerator to accelerate some electrons, and then to collide the rest of that beam with this group of accelerating electrons, such that in the electrons' frame of reference, their reference frame, the beam's peak power is much higher. It'll be zeta-watt equivalent. Oh, and doing this, you create pairs of electrons and positrons, as well as all the fun gamma rays and X-rays. So there's something that many people outside the laser community aren't aware of. This is a gain media competition. So there's many different ways you can amplify light, and which one will be used in the future. There are many different schemes and ideas to utilize particular technologies, and each have their own benefits and detriments, pros and cons. Dye lasers here pretty much lost. They've been phased out. They're toxic, corrosive, they're hard to work with, and they can't handle a lot of high power. Bulk lasers, bulk solid state lasers, are practically all that we've discussed this far. These are big, massive crystals, titanium, sapphire, neodymium, YAG, that's to be grown and very carefully controlled. The downside with these lasers is that they only operate at about a few hertz if you're lucky, so 1 pulse per second, maybe 5 pulses per second for the state-of-the-art systems. Then there's thin disk systems, which try to mediate some of this by using a thin piece of one of these big slabs and pasting it to a heat sink to help with cooling. These systems also have their own issues, beam quality, repetition rates. And then there's fiber lasers, which offer a unique approach to this problem, but you typically don't get very much energy out of a fiber laser. And you'll see which team I'm on here. So there are many benefits to using optical fibers. They're robust, they're cost-effective, they have low loss over long propagation distances. They can be monolithically integrated, meaning we can just splice them together. And they can be doped, meaning that when we're making these optical fibers, we can add different ions to them to turn them into amplifiers or gain media so they can be used to make lasers. And that is what my research group does. We do fiber laser chirp pulse amplification. And this is in a scheme called coherent pulse stacking amplification. This allows us to get spatial and temporal energy scaling within our system, circumventing some of the limitations of fiber optics. The near-term goal for our lab is to get 1 terawatt peak powers at 10 kilohertz repetition rates. So that's 1 terawatt 10,000 times a second. That will give us a kilowatt average power. And for some scale, that is a James Bond villain level type laser. So, like I said, we get temporal energy scaling, and this is through coherent pulse stacking. Instead of using 1 pulse, we use a train of pulses, and we get spatial energy scaling through spatial combining. We combine our train of pulses into one, and we can spatially separate into many different amplifiers, and then combine those back in space. And it may look complicated, but in essence, we are still just stretching, amplifying, and then compressing. This is what the spatial combining scheme looks like in the lab in a nice diagram. We have our signal come in from the top, and you use some polarizing beam splitters to create many different identical copies of our signal, feed those each into their own individual amplifiers, add energy, pump them, and then we can combine them using more beam splitters back into one beam here at the bottom, with some feedback going to our control systems, as much of this is electronically controlled. And here you can see what it actually looks like on the optical table, water cooling and all. And where things really get interesting is when we talk about temporal combining, when we combine this stack of pulses into one. This is done with Gears-Tournois interferometers, GTI stackers, and I have a diagram of one here on the right. It has 3 100% reflecting mirrors and 1 partially reflecting mirror, and that partial reflectance varies depending on the configuration we want to operate with. And we can stack trains of pulses into a single pulse. In our system, we have 81 pulses. So we start with 4 stages of these interferometers, and we can stack 81 pulses into 9, and then those 9 pulses into 1. And I have an animation here that explains this much better than I can. And my advisor made this. So we have 4 cavities here, and we'll start feeding these pulses in. And as you can see, these pulses begin to interfere with one another constructively or destructively, depending on the physics at which we've defined. And we do this such that when the last pulse comes through the cavities, it's able to pick up all of the energy of the other pulses. And there we go. Thank you, thank you. So we have 8 cavities in total, 4 short cavities to stack 81 into 9, and then 9 longer cavities to stack those 9 into 1. And this is what it looks like on the optical table at many iterations, many generations of graduate students later. This is a 4x4 multiplexed nested configuration, saves space and resources. So I've shown you a video of the physics. Now I can show you a video of what we actually see in time as we're running this system in the lab. So first we have our 4 short cavities. Look for solutions to stack those 81 into 9. And then once we have those 9 pulses, we can then oscillate our long cavities to look for solutions to stack these 9 pulses into 1. And just like that, we're ready for experiments. So we've talked about our pulse bursts and splitting them into identical copies. We stretch, we amplify, we compress, but what's next? At the end of our system, we have a pulse of about 100 millijoules of energy, so 0.1 joules, 300 femtoseconds. What more is there to do? This is where we get into my research, spectral broadening. So I've mentioned nonlinearity before, and I think this is the time to actually define that. So when I refer to optical nonlinearity, I'm referring to when high power light alters the optical properties of a material it's interacting with, which then in turn alters the light propagating through it. As you can imagine, it's very quickly you can get runaway effects because you have the material alter the light, which then alters the material, which then alters the light. So you have to be very careful when dealing with nonlinearities, which is most of the time why you avoid them. I plan to utilize them. And using nonlinearity, I want to increase the bandwidth of our pulses, making the ability to make our short pulses shorter, giving us the ability to make our powerful lasers more powerful. So the nonlinear effects in question here is the nonlinear index of refraction. This arises from the optical Kerr effect. So we have the standard index of refraction. Let me get the pointer back up. We have the standard index of refraction that you might expect with any material here. And for the rest of this talk, when I'm referring to nonlinearity, we'll be doing this in just basic glass. This isn't a special material. This is just regular old glass, silicon dioxide. But there's another term here, another term which is intensity dependent. And these terms depend on the intensity both spatially and temporally. Spatially, we can get effects like self-focusing. And this is when you send a beam into a material, glass even, or even air, if the beam is powerful enough, and it will turn this material into a lens. And this beam will begin to focus, and it will keep focusing until the math stops mathing, until you practically focus into a singularity. And the beam will then proceed to just drill its way through the rest of your material. Throw off tons of fun radiation. It's very pretty. You get a lot of colors out, but not useful for your material or for your experiments, at least the ones that we run. Typically avoided. And there's self-phase modulation, which arises from the effects of the intensity varying in time. So we have the pulse, which has a transverse profile, and those are the intensity variances in space. And then in time, just like I showed before, it varies, right? We talk about the full width half max. So there's a distribution in time, and that variance here leads to a broadening of our spectrum. It's a complicated effect, but in short, we come in with one color, we pass through a material, and we get a much broader bandwidth of colors. So I use them to increase the bandwidth of our pulses. And another fun effect of self-phase modulation is that it also adds a chirp to our bandwidth, to our pulse spectrum. And this means that we can compress them to far shorter pulses than we started with. So we take our input from the laser, 300 femtoseconds at about 10 nanometers bandwidth, full width half max. We pass it through this configuration called a Harriet cell. As the light passes through the glass, it accrues more and more nonlinear phase, more and more nonlinear effects. And then we couple it out, and we get the same duration and time, 300 femtoseconds, but with a much larger bandwidth. All we then need is to compress, and that same bandwidth will take us now down to 30 femtoseconds. So a 10 times increase in power. Sounds simple. That's why I'm here. It's fortunately not. But that's what I do. And that's what my lab does. And we started with some background in setting the scales at which these phenomena occur. And then we talked about some ultra-fast systems and the futures of them, what we hope to do with them. And we went into my research, my group's research, and what I do. Instead of avoiding, I utilize optical nonlinearity. And I'll leave you with some pretty pictures in the end of our amplifiers when we're pumping them, glowing a pretty color. I didn't have time to talk about the physics of them. This is what the inside of our amplifiers, this fiber, looks like. This is our beam quality at the end. So thank you again for coming out on Saturday and listening to my talk.
Thanks so much, Ty. So save your questions for Ty, because we'll do the question and answer session after the next talk. We're just changing over here.
Mm-hmm. It's all ready for you, Max.
We're not on screen, Ty. Okay, great. So Max now will tell us about taking the temperature of games and social hierarchies. Take it away, Max.
Hi. Yeah, I hope I'm coming through on the mic and everything. And hi, I'm Max. I'm going to be talking today about how we can define and measure the temperature of games and hierarchies across science. So I'm a fourth-year physics Ph.D. student working with Professor Mark Newman here at the university on networks in a broad sense. I also work with the Center for Complex Systems here at the university, where we basically try to use ideas from physics and all sorts of disciplines to talk about lots of things in a sort of a similar language. So that includes the topic of today's talk, where we're going to be trying to somehow build a thermometer for measuring hierarchies, whatever that means. So to get into that, let's first talk a little bit about hierarchies. So oftentimes these arise in the world of sports, and they're going to be talked about in that sort of language. So in this example, we have 4 boxers, numbered 1 through 4. And we're going to observe a series of matches between these boxers, maybe these 6 matches. And we're going to record who beats who by drawing an arrow from the winning boxer to the losing boxer. So for example, here, boxer number 1 beats boxer number 2, boxer number 2 beats boxer number 3, all the way down to boxer 4 beating boxer 1. Now we can aggregate these match results into what we call a network, really a directed network of these boxers, where again we have these arrows representing who beats whom. And from that, the task we're going to be interested in, oh, sorry about my clicker, is going to be trying to figure out who's maybe the best boxer. What's an appropriate way to rank these two, or these boxers, given these results? Now, of course, this isn't relegated to the world of boxing. We can apply similar things to, say, college football. So here I have a network which represents the results of the Big Ten Football Conference from 2022. And so each of these nodes now represents a different football team, and these edges represent the match outcomes between them. So we can see Michigan over there, and we can notice that all of the arrows are pointing away from Michigan, and that indicates that Michigan was undefeated in 2022, as in 2023. Of course, we can also apply this to other sports like chess. So in chess, oftentimes, different players you're given a rating, some sort of number which is supposed to indicate your skill. Higher number is better, and the way that we get the ranking of them is just whoever has the highest rating is considered the best chess player in the world. So not just in sports, but we can even apply the same sort of logic to animal dominance hierarchies. So here, these arrows now represent pecks between chickens. So the red chicken pecks the blue chicken, and some researcher watches these chickens, records who's pecking who, and then from this can try to figure out what the pecking order of these chickens is. And so, in fact, this is where this phrase pecking order comes from, this sort of animal behavior research. So, of course, for the chickens, this social world that they have is important and determines what they have access to. And by looking at who's pecking who and using these sorts of models, we can gain insight into that world without having to interview the chickens. Similarly, we can look at dogs. And so, an animal behavior researcher would look at a pack of dogs and look at two of them and try to figure out, okay, well, which dog is dominant somehow in this interaction? In this case, I think that they would say that it's the white and black dog that is winning this, since that brown dog doesn't look very happy. So someone would look at this and then be able to figure out the order of the dogs. And so we can also apply this to consumer choice data. So for example, say you're a soda company and you ask somebody, hey, do you prefer the red soda or the blue soda? They say that they prefer the red soda, and we're going to indicate that as the red soda has now beaten the blue soda. And so you ask a bunch of different people, between these two, which do you prefer? And then from this, try to figure out what, say, the best soda is. So you could imagine, a bunch of tech companies, maybe every time they show you two things and they record which one you click on, try to then infer what the best products or whatever they're talking about are. And so this sort of setup is known as a paired comparison study, and the very same framework is applied in that context. We can even get a little bit more creative about what we mean by winning and these hierarchies. Turns out, if we maybe ask a bunch of high schoolers to list their top 5 friends, most of the time, friendship is seemingly not a two-way street. The people who you list as your friends very frequently don't list you back. And so you can call this sort of asymmetric interaction like a win in the same context of these other situations. And since somehow, if I say that someone is my friend, but they don't say that they're my friend back, they're cooler than me, they've beaten me. And in that interpretation, you can figure out maybe what the hierarchy of this high school is. What are the coolest people? And so this is something my advisor had done with high school data. And so again, each of these little dots represents a student. And we can see that there's the uncool middle schoolers on the bottom of the hierarchy and the cool seniors on top. And so you see this very pronounced structure under this sort of interpretation. We can also get a bit creative and talk about university faculty hiring. So if I graduate from the University of Michigan, hopefully with a Ph.D., and then I get hired as faculty at, say, University X, that's kind of like Michigan has beaten that other University X, because that institution, which hopefully hires me, respects the fact that I got a Ph.D. degree from the University of Michigan. So somehow by using the same sort of framework in this setting, we can infer some hierarchy of clout and of prestige. And so researchers have taken this sort of approach as well. And as you might imagine, there's a pretty strict hierarchy among universities, and oftentimes people get hired sort of downstream in this hierarchy of prestige. And so you can infer that, again, using the very same methods. And so the reason why I'm going through all these in rapid succession is I want to emphasize that there's this analogy between all of them. Really, instead of talking about sports, animals, universities, we can just abstractly think of these as some objects and define winning and losing between them in however creative way we like. And then from that, oftentimes what we'll observe is some sort of hierarchy among those objects. So Specifically, the math that we're going to use to analyze these systems is something known as the Bradley-Terry model. And in this model, we're going to assign each person, in this case each player, some score SI, so S for score. So in that chess example I gave you before, these numbers over here were these scores SI. And the key idea behind the model is that we're going to take win probability. So I take two players, I put them in a room, and I ask, what's the chance that this one beats that one? I'm going to take that probability as to be a function of the difference in the scores, the difference in the strengths of these two players. And so specifically, we're going to use this form. So if we have player I, player J, then this win probability will take it to be a function of the difference between their strengths. So specifically, we're going to use this function right over here. It's known as a sigmoid or a logistic sigmoid. And the nice thing about this function that we can check is that if, suppose, I'm evenly matched with my opponent, there's no score difference between us, then that's a difference of 0, and we see that my win probability is 1/2. That's what we'd expect. It's 50-50. Nobody's better. If instead I am much better than my opponent, I have a large positive score difference on them, then I'm very likely to beat them. My win probability goes to 1, and then on the flip side, if I'm much worse than them, my win probability should go to 0. I really don't have a shot. So to make this a little bit more explicit, I'm going to introduce you to my friend Kapil. He's a math Ph.D. student at the University of Chicago and the best chess player that I know. Unfortunately for Kapil, he's playing against Magnus Carlsen, who is the very best chess player in the world. And Magnus has about 500 points on Kapil. So we can plug that into our model and find that according to our model, Magnus Carlsen should win this match 95% of the time. Now that's great. How do we actually find these scores? Oftentimes the ways that these are done, and also I should mention these are often known as ELO scores. The way that this is done is that if you win a match, your score is going to go up. If you lose a match, your score is going to go down. And the important part about this probability is that it's going to inform the amounts by which these scores go up and down. So if we suppose that Magnus Carlsen does what he's supposed to do and beats my friend, he's going to gain 1 point, and Kapil is going to lose 1 point. On the other hand, if Kapil pulls off the upset, he's going to gain 20 points. And so because of this win probability of 95%, the ratio of these two amounts is sort of the odds ratio. It makes this a fair contest. If they play a bunch, there's not going to be some net transfer of points between them. Cool. OK, so the main point of this talk that we're going to dwell on is where did this function come from? I just sort of pulled it out of a hat. But it turns out that we can find it in physics, and we're going to use physics to then motivate a way to generalize this model and define what we mean by the temperature. So to do that, we're going to first talk. So this function, it turns out it shows up if we heat up electrons. So to get there, let's first talk a little bit about electrons. So as we might know, atoms have a nucleus that's then surrounded by electrons. And these electrons are going to fall into energy levels, indicated by these circles here. And generally, the electrons would really like to be close to the center. That's the lowest energy configuration. But because they're these fermionic particles, which means a variety of things, but for us, the important thing is that they can't intersect. They can't go on top of each other. As we add more and more electrons to the system, they're going to be forced into higher and higher energy levels that they really wouldn't ideally like to be in. So this is known as the Pauli exclusion principle, and we can see it here. If we start to just add electrons, they're going to be forced to occupy those higher energy levels because they can't just be on top of each other. So we're going to have a really cool demo here today, and that demonstrates this. But we're not going to be able to show you a bunch of electrons, so we're going to need some sort of substitute for electrons. We're going to use metal balls. And metal balls are going to possess a lot of the important properties for electrons that we need to see this function. So for one, they can't intersect either. And so what we can see is that, this might be obvious, but as we add more metal balls to a system, the metal balls would like to be at the bottom, the ground state, but just because they can't go on top of each other, as we add more and more metal balls, as we add more electrons, they're forced into higher and higher energy states. So that's going to be the important property that we need to capture this fermionic statistics. So just as we add more metal balls or more electrons, we can observe that. And so the other ingredient, now that we're able to model electrons in a reasonable way, is that we need to understand temperature. So oftentimes, when we're going to heat things up, whatever we're heating up is going to be moving around more. So for example, if we take water, we put it on the stove, that water is going to boil and it's going to move around, and that's how we know it's hot. If we look at a molecule that's heated up, then if we looked really closely, we'd actually see that these atoms are vibrating and bouncing around a lot. So the way that now that we have our electrons and our ingredients are electron and temperature, the way that we're going to heat up our electrons is we're just going to shake them around a bunch. So Monica Wood and the wonderful lab demo team have actually created a custom experiment for this talk today. And so just to explain a little bit about how it works, we've got a lot of little metal balls in this plane. So hopefully it'll show up soon. But the general idea is that it's very similar to that tube where the metal balls would really like to come down to the bottom, but it's this angled plane. But what we're going to do is we're going to start to increase the temperature, and we're going to see that not all the balls are able to go, have this. So we observe this sharp transition where there's no balls, and then there's a bunch of balls. But then Monica wants to take it away. Yeah, so what we end up seeing, and so I'll sort of now analyze that if we go back to the slides. So what we have shown on the sides is a recording of that happening, now turned on its side. And what we can do is we can actually count the number of balls at each horizontal position. So because this is an angled plane, each horizontal position corresponds to a certain amount of energy that ball has. And so before we turned anything on, we had this very sharp transition between no occupancy and full occupancy. And so this transition point is also known as the Fermi level, if this were a sea of electrons. And as we increase the temperature, this transition becomes smoother. We have this transition from no occupancy up to full occupancy, and it's not quite so sharp. And as we continue to increase the temperature, this is going to be a more gradual transition. There's all sorts of confounding factors in this setup, the warp of the plastic, the static electricity. If we had everything perfect, it turns out that we should have this orange curves that I've plotted here on these still shots. And this curve is known as the Fermi-Dirac distribution in physics. But you might know it by another name now. It's also the logistic function, which this model is built on. So the important thing here is that by just looking at one of these pictures of our system, we can fit the data we observe on the number of ball counts and basically infer what the temperature is. This distribution is low temperature, this distribution is middle temperature, this distribution is high temperature by looking at the spread of them. And the core idea we're going to use is that we can use a very similar technique to take the temperature of these different hierarchies. We can figure out what is the most appropriate curve to use in these different settings to somehow define what that temperature ought to be. So to make that a bit more explicit, our Bradley-Terry model is built on this particular form of the function. But if we consider this Fermi-Dirac distribution at different values of the temperature, really often in physics we like to use beta, 1 over temperature, inverse temperature. Then this functional form is going to now have this beta term. And so we can see if the temperature is 0, it's this very sharp transition between no occupancy and occupancy. But as we increase the temperature, that is going to become smoothed out. So by generalizing our model in this way, we can recover our original model for a very specific choice of the temperature. But by allowing it to vary, we can just fit the temperature to the data that we observe and thus define what we mean by the temperature of a hierarchy. So I'll also mention that this is sort of part of a broader analogy between temperature and noise and statistics and physics. So to complete our story, we're actually going to pull a technique from statistics known as Bayesian inference. And a key part of Bayesian inference is that you need to make clear your assumptions. So specifically, we're going to assume that the spread of the scores is roughly 1. So if I just take 2 random people, their difference is about 1 score. You might have noticed before the chess players had a difference of about 1,000. We're basically just setting the length scale of our problem by doing this. So by doing this, then we actually gain another way to interpret this beta, this inverse temperature. Besides just being sort of the convention in physics to use, it turns out that we can interpret this inverse temperature in this context as a measure of the number of levels of stratification in the hierarchies that we observe. So how do we see this? We can ask, in a given game, how much better do I have to be than somebody to beat them reliably? Say beat them 75% of the time. So we can check in this case, if we have a system that has beta equals 1, then this is going to require a score difference of 1. I need to be 1 score better than somebody to beat them reliably. So again, because that was sort of our typical score difference between players, we could say that in this game, there's just one level of separation between players. So you can imagine this is maybe a game like tic-tac-toe. I think I'm pretty good at tic-tac-toe. I don't expect to lose at tic-tac-toe, but at the same time, the only people who I'm going to beat at tic-tac-toe are those who truly have no idea what they're doing. There's the people who know how to play tic-tac-toe, and there's people who don't know how to play tic-tac-toe. It's a simple game. Now we can compare that to maybe a different game, which might have beta equals 3. So in this same situation, if I need to beat someone reliably, I only need to be a score difference of 1/3 better than them. So I take the same typical separation, and I can now fit 3 levels of play between these same players. So this we would call a high-depth situation, and you can imagine this is more like chess. I'm not particularly good at chess. My friend Kapil will reliably beat me, but Kapil will be reliably beaten by Magnus Carlsen. There's more sort of opportunity for stratification in a game like chess. All right, so now that and of course if we use sort of the thermal interpretation, this would be a hot hierarchy, and this would be a cold, rigid, frigid hierarchy. Great, so now that we've defined this idea of depth, this idea of temperature, and we understand where it hopefully comes from, we're going to consider, I'm going to show now all of those hierarchies we considered at the beginning along this spectrum. So of course, because this beta inverse temperature is 1/T, these low values of depth correspond to high temperature, and these high values of depth of beta correspond to low temperature. And so first we consider a variety of sports. We use this method, this thermometer, on Scrabble, basketball, chess, tennis, soccer, and video games. And we find a good deal of variation. We have our chess, we have our tic-tac-toe. But in the grand scheme of the hierarchies we consider, they're actually all relatively low depth, high temperature. Because as we start to extend our consideration to maybe the human social hierarchies, such as the friendships, the universities, suddenly these become much more stratified hierarchies than we observe in sports. They're stricter. And if we go into the animal world, we can observe, we can find extremely strict hierarchies all the way up to the hyenas. So, really what this is saying is that the top hyena will never lose to the number 2 hyena, but the top Scrabble player will, very often just lose to the number 2 Scrabble player, effectively. And the thing that I think is really cool about this sort of, this thermometer that we've built is that we're not telling it that, oh, this data set comes from sports, this data set comes from humans, this data set comes from animals. But yet when we measure these temperatures, we see a very clear separation between the sources of the data. And so we have various sort of speculations as to why that might be. For one, why are the sports all relatively low depth, relatively competitive? And that might just be because if you hypothetically had a very high depth sport, a very predictable sport, then it would be sort of boring just to play or to watch. If you always knew who was going to win, or all the matches you saw were just trouncings, no one would want to really play or watch that. And so, for example, there's leagues like the NBA in basketball, where they have a draft lottery system where the team which performs the worst in any given season is going to then have the opportunity to select better players. And so this is a way to kind of bring the teams in closer competition so that it's more exciting and people like to watch it. So there might be similar sort of feedback mechanisms which are not having us observe these very deep games. So also by putting everything on the spectrum, you might also say that somehow having more levels of social stratification is a bad thing, and that it's kind of sucks to be a hyena and it's fun to play Scrabble, but getting hired as an academic is somewhere in between those two extremes. So just in summary, we've made a very simple generalization of an age-old model using physics as our inspiration, We've combined this with methods from statistics to gain new insights, not just about, say, who's the best chess player, who's the top chicken, but to be able to compare these different hierarchies to each other. And by now having a way to measure social stratification or inequality, perhaps we can better understand its causes in these different settings. So I'd like to thank my advisor, Mark Newman, in the physics department for my co-author on this paper we put out on the subject, NSF for funding the research, of course the Saturday morning physics team for putting all of this together. And in case any of you like to code and have some creative ideas, we put out a Python package implementing these methods as well. And yeah, so thank you all so much for watching. Yeah.
Okay, great. Thank you, Max. And Tayari. So we're going to move to the question and answer period. We have a few questions from online. And you guys both have microphones. There's one over here. So normally what we do is have you come to the aisle if you have a question. But I think today what we'll do is run around the room with a microphone, okay? So if you have a question...
We're grabbing them. Hey, Tim, we're grabbing.
Can we grab this?
If you have a question, please raise your hand, but I'm actually going to start.
Let me bring up my stuff.
I have actually a question for both of you, or each of you. And that is, what got you interested in studying physics or applied physics or even complex systems? Maybe Ty should start?
For me, in particular, applied physics. I was a physics undergraduate. We can go back to high school. I took engineering classes. I always liked building things. And after taking a few engineering classes, I realized engineering wasn't for me. It wasn't enough. It didn't go deep enough. And then after I took a physics class, I very quickly realized, okay, this is something I like. So I took the physics classes at my high school, and I decided, well, become a physics major. And then through my undergraduate, I learned about lasers. And they kind of brought together all of the things I liked, electronics, optics, and they're big and powerful, and pretty colors. Like, this is cool. And then I did a internship here, and I got to learn about the Zeus laser and the Hercules laser and see some of these systems. And it just captured my imagination.
Cool.
Yeah, so I guess I've always sort of liked math and just had fun with it. So I've been on a bit of a journey figuring out like what fun, real world things you can do with math, and physics is definitely one of them. And particularly working with complex systems, I have had a lot of fun with not just applying physics and math in a general sense, but being able to talk about all sorts of different things in a unified way has been really cool. So.
Neat. Actually, I want to just emphasize this demo again. This was Max's idea of how to demonstrate this. It had not existed before a few weeks ago, and with some discussions and a few iterations, Monica and her team put it together. And I got to tell you, it is really awesome, so they deserve... But in a way, we've come to expect that. So, okay, and then the other thing is that the analysis of the graphs that Max showed, I believe that you got this working on Thursday, and Thursday night, Max went home, maybe, maybe not, and wrote the code to analyze those data pixel by pixel and show where the balls were as a function of time and at various temperatures. So, I mean, that's pretty amazing. Okay, so we have some people in the room who would like to ask questions. Why don't we start over here?
A question for, and I hope I get it, Tayari?
That's right.
Yeah, and it has to do with lasers and fusion energy and what type of lasers are currently being used to ignite fusion energy, and how your findings relate to that or embellish on that.
Okay, great question. Ultrafast optical systems are being considered as the drivers for fusion physics moving forward in the future. They are not quite there yet. The current lasers that do fusion are ones like NIF and Lawrence Livermore. And these are not ultra-fast optical systems. These are fast systems, so nanoseconds. So milliseconds, microseconds, nanoseconds, so 10 to the negative 9. Much longer pulse durations, but by using a longer pulse duration, they get many, many orders of magnitude of higher energy. When I say high energy, I'm referring to 1 joule, and they have megajoules, kilojoules of energy, and they're able to squeeze that into very small spaces to promote the fusion of the atoms they've put in there. So these systems are being looked towards fusion in the future, especially higher partition rate options, and that is partially why we developed this science further. Did that answer your question?
Question over here.
All right, nice job, both of you. I just have a couple quick questions. So it's Ty, is that right?
Yeah, sure. Yeah.
So do you want to do something entrepreneurial with what your research is, or I was just kind of curious of when your intro that was something you do?
Can't do anything entrepreneurial with this yet, not while I'm a student. Although there are possible patent options in the future for some of the things my lab has developed. We've patented things in the past. My advisor started companies with some of his research, and we have patent plans in the future. I work on things entrepreneurially in my free time. I actually make and sell these belts here.
All right. You need a QR code.
Yeah,
on
I
the
should
slide next time.
have put it up there.
And then Max, do you do any sports betting?
I don't.
Well, can you use that to, because like in the history of probability, the mathematics of probability, oftentimes the mathematicians who predicted the probability would beat the house, and they'd actually self-fund and they could just do math for free their whole lives. I just wondered if you've considered that.
Yeah, I mean, so one thing about these models is that they only look at who wins and loses. So if you were really interested in sports betting or specifically analyzing any one of these contexts, you could build, the sports bettors know, okay, the quarterback's injured, that's going to decrease their chances. We don't incorporate that in these models, so we deliberately have a simple model that just takes wins and losses because there's not really an equivalent to the quarterback being injured when we're talking about the baboons interacting. So
Awesome. Well, I'm always looking for someone to beat the house, so.
Sure, yeah, maybe
Thank you.
someday.
Hi. I had a question for Max. I was wondering if you could elaborate a little more on the Fermi Dirac distribution for electrons specifically as like a complex system.
Yeah, I mean, so really it's, in the analogy, we have score is energy in this case, and it's just, if you take a bunch of fermionic particles and you heat them up and you observe this, usually it would be a continuous distribution, but it's generally like whenever we have these fermionic particles, and really the key idea that makes this distribution show up is that they can't go on top of each other. Since if you had things which could go on top of each other, like maybe bosons, and you wouldn't have this sort of region of full occupancy and then a cutoff. So when you have that effect, which we sort of hopefully were able to demonstrate with these metal balls, then you expect to see this sort of statistical transition. So I hope that was enough detail. But yeah, it's very important for the theory of lots of physics. Most of the things we care about are fermionic particles, so that distribution shows up all over the place. But
Can I ask, I'm just going to inject here and say, how do you deal with ties in these? So,
yeah, so usually you would model that in a separate way, which includes the possibility of ties. Like for example, really in chess, oftentimes when people of similar skill play each other, it results in a tie. And so you can use a slightly generalized version of the model I showed you, which basically says if people are similar in skill, you could observe this third outcome, which is a tie. So for example, even in the friendships, we actually model reciprocated friendships as a tie instead of a win. So it just makes the math slightly more complicated, but you can sort of still interpret things in the same way and define the temperature. But yeah, a lot of these settings have these ties. So.
question over here.
Oh, I'm sorry. Well, I'm Chengming Fan, University alumni. I'm so proud of you, Max and Ty. And Max have first question, maybe just for fun, or maybe you can do the prediction using this hierarchical analysis in social things. As you know, November we're gonna have new president, or who is gonna win? Can you do that using?
Yeah. So just in the same way that I showed my friend Kapil and Magnus Carlsen playing, and it gave them each a probability. You could use that. You could interpret that as a prediction that the favorite will win, and you can check like how often are these correct. And it turns out that if you use our more general model, you are actually correct more often. Like you have more predictive power. I think it's on the order of like 2%. Like maybe instead of getting it right 80% of the time, we get it right 82% of the time. So you can interpret it in that way. And sort of maybe that would be more relevant to sports betting, for example. For us, we're sort of, even though the model is better, we're kind of interested in how can we then use it to compare all these different things to each other. I hope that answered your question. But yeah, you can use this for prediction.
Who's going to be the president, next president?
President. Oh, wow. Well, I think,
I'm just kidding.
People have used this sort of model for politics data. Like they ask people, it's sort of the paired comparison studies I was talking about before. Instead of asking people which soda do you prefer, you ask people which politician do you prefer? And then you come up with a ranking of the politicians in that way. We didn't end up including that data here, but you can apply the very same methods to that. A lot of it is just a matter of sort of creatively defining what you mean by a win. I'm not sure who's going to win the presidency, but yeah.
I'm just kidding.
But yeah,
well,
thank you for the
I want to
question.
thank Ty, and a quick question is that some of you may remember we heard a chirp, and we have this laser using this technology, as you know, the LIGO, L-I-G-O, in this building. What my question is related with laser interference, gravitational wave analysis observatory. That's far, far away. So if you can help me understand how it is the pulse manipulation using laser is only valid for short distance. Am I right?
If I understand your question correctly, are you referring to
Distance.
between two pulses interacting with one another?
I'm talking about not in a lab, not in the near field,
So like LIGO.
light years ago.
Well, yeah, when we interfere, we can build something called an interferometer, and we talked about Gear-Tournois interferometers. When we build these, we look at how these waves overlap and how that changes as you can affect the delay line, the stationary arms. We can move these waves in and out of phase with one another. So as I understand how LIGO works is you have these two arms in different axes, and I can figure that out, in two axes. And when you have a gravitational wave come and change one axis, you're able to look at the interference as these different waves shift in and out of constructive interference with one another. Was your question referring to optical pulses? Because there's a different. Okay, sure. That's it. Okay, sure.
Yeah, cool. So a chirp, as he said, I'll just reiterate, is actually, and this relates to a question that came in. So maybe I'll just ask the question, and then we'll go back to this. And are chirps always from low frequency to high frequency?
No.
And are they always from low intensity to high intensity?
They are always from low intensity to high, in the sense that you have a pulse envelope. Oh, I take that back. Chirp, as defined here, it gets very complicated. There are higher order terms. Chirp is the second order term. In time, it's the first order term. But there are other terms you can look at in this series of terms where you don't just get a linear variation in frequency with respect to time. That's why it's called a linear chirp or an up chirp. It can go either way. You can have an up chirp or a down chirp. You can have the shorter frequencies in front, or you could have the longer frequencies in front, or you could have more complex phase distributions where you have different distributions of frequencies throughout the temporal profile. I didn't have the time to talk about that, but it gets very intricate, let's say. Yeah.
And it can happen with gravitational waves and lasers and sound. All of those are chirps. And we saw,
Yeah.
I guess, 2 of them today, sound and light. Okay, question over here.
So for Max, some games like chess, you really just have the skills of the players. Other games like Scrabble, there's a random component because what letters are drawn is going to affect the outcome. Other games like Magic the Gathering, you know, everybody's starting with a different deck, and so decks may be more powerful or less powerful. Plus, you've got the randomized element of drawing cards, plus you've got the skill of the players. How does that complicate this kind of hierarchy?
Yeah, so actually in the full model we used, we sort of defined a notion of luck in this sense, which might sort of get at what you're talking about. We could instead model what's going on as there's some part of our system which is governed purely by luck. So we flip a coin, and with some probability, our outcome is decided by a pure flip of a coin. With the other probability, we play a game of chess, which we sort of take as an example of something that truly has no luck. And so if you sort of set things up in this way, which is a slightly more complicated thing, you get a picture that looks more like this, where you can differentiate this notion of inherent luck, so sort of luck which no amount of skill can overcome, versus this depth, where the blobs here represent sort of reasonable parameter values. So maybe that sort of gets at what you're.
It does.
Okay.
I'm seeing these as streaks. I see, like, I'm looking at the basketball line, and I'm looking at the mice line, and I'm looking at the vervet monkey line.
Yeah.
And it seems like we have no clue how much luck there is in basketball. Mice have a lot of luck, and vervet monkeys have little luck. Am I reading that incorrectly?
Yep. Yeah. Yeah. So a part of it is like systematically, if we have a very shallow, like this sort of statement about luck is something about what happens when you have a very large difference in skill. Do you still have some probability to pull off the upset? So if we're talking about, say, a low depth environment where people are very tightly packed, you just don't have a lot of observations of like really strong people going against really weak people. So that's sort of why systematically we don't have a great idea of how much luck there are in these shallower situations. But that's sort of the distinction we draw here. It's slightly more complicated, but we do have a bit more of a multi-dimensional picture of what's going on in these. But yeah, I think it's really an interesting question, and like how exactly should you define these different axes of game mechanics and things. So yeah, thanks for the question. But
Interesting that academic departments and baboons have so much in common.
yeah.
Question over here.
Yeah, I actually have a question for each of you. I guess, Tayari, my name is Eli, and so I'm curious about the Eli laser. Yeah. So I guess, like, what does it stand for, and like, what is it that it does mostly?
Oh, that's a good question. I forget that acronym. Extreme light. That might be it. Extreme light something. They get very creative with these acronyms. It's Europe's most powerful laser, if I'm not mistaken, and it's run by a series of countries. I have friends who go to Europe to do experiments on the Eli system. It's 10 petawatts, I believe, as of currently. So it's the laser we have here at Zeus, which we just got up and running, is currently operating at 1 petawatt. Eli is at 10, so there's a lot more power over there, as well as 1.5 kilojoules. So depending on the experiment you're running, sometimes you need higher energies. The pulse duration isn't as important. Sometimes it's the peak power, and sometimes it's a pulse duration. And that depends, are you using this to accelerate electrons? Are you using this to ablate a material? Are you generating neutrons? There's many different ways to utilize these schemes.
Gotcha. Cool. Okay. And then, sorry, I had one question for Max. Max, my question was about the sports like basketball and soccer. I am assuming that you're analyzing like hierarchies based on teams, but I'm wondering about like individual players, and if you are able to analyze individual players, does the temperature read similar to the teams, or is there a difference there?
Yeah, so I guess temperature fundamentally is a measure of the spread in skill somehow. So You're right, we're looking at the teams, since the teams are the ones doing the winning and the losing. So if you had some way of defining that this player has beaten that player specifically, then you could apply it in that setting. Intuitively, I would imagine that there is more range and skill among individual players, since somehow when they're all on a team, their skills are kind of aggregated, and generally things get closer together when we aggregate them. But yeah, we hadn't considered that, but there's many interesting research questions. So, but thanks for the question.
Thanks.
Hi, I had a question for you, Tayari.
Yeah, sure.
Could you elaborate more on like some of the like material science advents that take place amongst like the game mediums you talked about, like maybe the fibers and specifically the crystals?
Yeah.
Because I'm guessing there's like a lot of innovation happening there. I just want to know.
There is. That's a great question. I even have a backup slide to go into a little bit of that here. Yeah, here we go. So these are the fibers we use in our labs for our amplifiers. My advisor invented this technology, chirally coupled core fibers. So in building lasers, there's many different things. There's the power, the bandwidth, right? The energy. But then there's also things like beam quality that are very important. Because if you don't have high beam quality, if your beam isn't the right shape spatially or even temporally, you won't be able to compress it in time cleanly or focus it down in space cleanly. So another benefit of fiber lasers is that in this current configuration, all of our beams are of the fundamental mode. It's the approximately Gaussian beam profile, which means that we can get the smallest spatial size when we focus the beam down. This is done with using this chirally coupled core fiber. Usually with optical fibers, if you want them to stay single mode, they need to be very small, very thin, literally the width of your human hair, the core of this fiber. 6 microns to 10 microns, very, very small. These fibers, on the other hand, are 85 microns, their core is in diameter. And when you increase the size of the core, there's a possibility for other modes to exist besides the fundamental mode. And this architecture here with the chirally coupled core, you have an octagonal core, which is spun with many side cores spun around it. This is able to strip out the higher order modes, allowing just the fundamental to preferentially receive the gain in these. There are other architectures like the thin disk lasers as well as the bulk lasers that are trying to utilize this. To my knowledge, fibers hold the record for being able to produce the cleanest beam qualities, but there are different ways you can massage your beam to get the appropriate qualities, at least in the near or far field. And there's a lot of innovation going on in terms of laser gain media. The battle is not over. I'm definitely, on Team Fiber. That's where I see the future going, especially because these systems are so much more efficient. We can get many tens of percentages of wall plug efficiencies using fiber lasers versus these big bulk solid state lasers where we're 0.001% efficient. Wall plug, like plug into the wall efficiency. But there are benefits to these big systems, and that's the immediate access to large sums of energy. And there are new gain media coming out, bulk gain media that you can, just with one single amplifier, you can get hundreds of joules of energy out.
Thanks so much.
Yeah, sure thing.
Peter?
Great speech by both of you. It makes me so positive and optimistic for the future of humankind, knowing that you guys are the future. And being able to explain such complicated things simply really demonstrates a command of the topic. So commend both of you for a wonderful speech. Question for Tayari. You mentioned someone had asked a question about fusion energy earlier. You had just mentioned something about energy output. How do you see the work that you're doing impact the existing grid and the power that we supply to our country? And this could be a real breakthrough, I think, in that space.
Yeah. So with fiber lasers in particular, we talked about they're cost effective. They cost much less to manufacture just because of telecom, and we transmit data still through optical fibers. And because of their high efficiencies, they also use less power. They're also going to be monolithically spliced together. all of this culminates in a much more efficient and compact package for their uses. So some of the things we want to promote, especially with the higher repetition rates, is uses in places maybe not in the hospital, but adjacent to the hospital. And this could help with the targeted radiation therapies or high-resolution x-rays to be much more portable systems that are much more efficient in operation. I don't know of any titanium, sapphire, big bulk lasers that are movable. You build them, you sit them down, require high levels of precision, very expensive parts. I mean, Zeus is a $100 million project. It's very expensive to build these big bulk systems, and we want to combat that with something more practical.
The ability to step up energy, though, the way you do with the phasing and the is that something that we could see introduced into the grid, and what would be the main impediments that you'd see to that mass application of this?
So yeah, the temporal energy scaling, I don't think would be beneficial to the grid directly, at least, because this is primarily for. Well, no, I take it back. Another reason that these amplifiers are designed the way they are, and one of the reasons that we actually have, I didn't get to discuss it in the talk, but here, you notice that train of pulses they're not all the same amplitude. There's a shape to that train. That shape has been carefully tailored such that when we pass through our amplifiers, we are able to extract nearly all of the stored energy within them. This is one of the reasons why our lasers are so efficient, is because we can really extract the stored energy from these and then stack these pulses back into one. This would not be possible with one pulse because we might blow the amplifier up or just heavily distort our beam due to different nonlinearities. So temporally, maybe not. I'm not sure. And temporally how this could be used for power transfer. Maybe there are applications in data transfer, data integrity, and quality. Spatially, I can see different use cases for this because we can just split our beam up into identical copies and then add on more amplifiers, which is one of the reasons why I really like our current architecture. We currently demonstrated, I think, 30 millijoules at 2 kilohertz. So not at our terawatt level, but many gigawatts of power. And now we've demonstrated that, we just add more amplifiers. So that's what we're doing, adding more stages. Currently the goal is to get to 12 stages. That should get us to 1 terawatt peak power at 10 kilohertz. And then after that, 100 stages, and then after that, 1,000 stages. We want to have multiple joules here. And as we continue to nail down the physics, the problem simplifies down to let's just do what we've done and just almost like Legos, plug more in. Yeah.
A question for Max. I'm actually in the sports business, so this is fascinating to me. Probably one of the key elements is the data set that you have, and so the N size is particularly a problematic issue because generally N size is pretty small. Also, I was wondering if this. My question is, does this Fermi distribution application, does that solve like small sample sizes, or does that? And then the other question I have regards to that is the recency bias one would have. The data being older, there must be a lot of decay.
Yeah, so I guess to answer the first question about the Fermi-Dirac distribution, really we use it as a way to motivate a more general model, but generally, if we don't have a lot of data, there's always going to be some fundamental limitations as to what we can infer. So before, when I was showing those like sort of big cloudy plots, that's really the space of all our errors, basically. And so the more data we collect, the better of a job we can do at pinning down exactly what is the depth, who is going to beat who, things like that. So there's always going to be some error when we don't have a lot of data, but if we make sort of nice modeling assumptions, hopefully we can do our best to mitigate that, but we can't entirely eliminate it. Sorry, and then I think the second question was about
recency bias.
Recency bias, yeah. So the method that I showed about ELO scores and how you sort of sequentially update them, where if you win, your score goes up, you lose, your score goes down, that would care about the order that you do things. It turns out that we don't actually use that method in our model. Rather, you take, say, a whole season of data and you holistically look at it all at once. And you ask, what are the rankings that matter, that make the most sense, sort of over the course of the entire season? So when you do things in that way, there isn't this recency bias. It's just asking a question about, in this particular time interval, who did the best overall. But you're right, the version I presented would have this issue. So,
Thank you.
yeah.
Question that someone raised about who's going to win the presidency. You know, we've had a lot of issues with polling and predictive analysis on the polls have been very, very skewed. We've been surprised. I guess it's because either people lie or the wrong question is being asked. Does your work imply that we could have something that corrects for that, or how do we think about bad data, I guess?
Yeah, I mean, I think a big part of sort of, you know, around, say, the 2016 presidential election, there was a lot of controversy about many polling agencies maybe, or, you know, rating aggregators being overly confident. And so I think a really important part about doing work like this is, you know, hopefully making nice, clean models, but also being very honest about what the uncertainties are in our models and how those uncertainties, say, in our data propagate into our uncertainties about the conclusions. So I sort of cheated and didn't do that. Like when I was showing you, okay, we can neatly put everyone at the specific point in the spectrum, that's not the whole story. Really, there's, you know, some uncertainties on all of these things, and really a more complete picture would have been to show you those clouds from the start. But that being said, it sort of comes back to the original idea of there's always going to be some amount of uncertainty, but by making nice modeling choices, such as, you know, hopefully the ones we've done here, you can try to make the best compromise you can. But there's some fundamental limitation. And you're right, in the polling context, you know, they use methods where they try to sort of see, okay, this pollster is systematically biased Republican or Democrat, and so you can use all sorts of tricks to try to mitigate this, but fundamentally you need to sort of be honest about what your uncertainties are, since,
Thank you, guys.
but yeah.
Now, just staying on that topic of politics for a moment, the data being what people respond to polls is one thing, but then all the elections that we've had, say, in this country, say, congressional elections, et cetera, have you thought of looking at that in terms of the temperature of an election in the United States, so to speak?
Yeah, I mean, I don't want to overclaim in terms of how broadly we can apply these ideas, but if there's ever a setting where you can call things wins and losses, and that's a reasonable thing to do, then you can define this notion of temperature. Really, it's just a different way to talk about sort of the variation in whatever population you're looking at. But I could imagine that. I mean, a lot of the examples I showed, like faculty hiring, like interpreting friendships in this way, are rather recent applications of this model, which has been around for a century. So like, I'm sure there's many creative ways to formulate the data such that a model like this would be helpful. And so, but yeah, I'm not aware of specifically for that application, but I think there's a lot of opportunity for creativity, so.
Great. Well, with that, I want to thank both of you and note what a great future, as also you noted, science and we all have with people like you. And thanks so much for giving these presentations.